Hi, everyone, and welcome to GIA's Knowledge Sessions, a series of seminars and talks all about gemology fueled by our decades of research. At GIA, we consider ourselves incredibly fortunate to study and learn from gems, and it's our mission to share our discoveries and learnings with the world. I could not be more excited to kick things off today. My name is Natalie Jaden. I'm the Content Marketing Manager here at GIA, and today I am joined by not one, but two very talented experts. Dr. Evan Smith is a research scientist here at GIA, and Dr. Aaron Palke, the Senior Manager of Research. And with that, let's kick off today's talk. Dr. Smith, take it away.
Thank you very much, Natalie. So today we're talking about minerals that have been described, discovered, and actually named by GIA scientists. So before we get into this story, I think we should talk about the word itself, mineral, and what this really means. The technical definition is actually a little bit complicated and kind of fuzzy around the edges, to the point that actually entire journal articles have been written on the definition of a mineral. But from that paper, here's sort of the most general sentence. In general terms, a mineral is an element or chemical compound that is normally crystalline and that has been formed as a result of geological processes. So even that is a little bit complicated, but there are three main ideas embedded in this as to what a mineral is. So this is a solid material that occurs naturally all around us on the Earth and even in space. This is stuff that has a particular chemical composition and a specific atomic structure. So the atoms are arranged in a repeating pattern in 3D that you can describe. And these are the things that define each unique mineral. Here are a couple examples here. Diamond and graphite. These are crystalline solids that you find in nature. They have a particular chemical composition. These are both made of pure carbon. And when you get down to the atomic scale, these carbon atoms are arranged in a specific 3D pattern. So diamond has a crystal structure like this, and graphite has a crystal structure that's different. It's arranged in these layers like this. So even though they're both naturally occurring solids that are pure carbon, they have different crystal structures. Therefore, these are two distinct minerals. So that's technically what a mineral is. The word mineral is also sometimes applied in other places where the meaning is a bit different from this. So what is not a mineral? One thing is dietary minerals. So things like calcium, when we're talking about nutrients and vitamins and minerals, this kind of mineral is a little bit different. This isn't the same kind of mineral that we're talking about in terms of geology, like those three major criteria on the previous slide. The other thing that can be kind of confusing sometimes is so when we start talking about gemstones, a lot of gemstones are minerals, but the names that we use to describe individual gem species, they're not always minerals in their own right. So some gem names for varieties of minerals are technically not mineral names. If we look at something like beryl as an example, these are three different kinds of beryl here, but they're all beryl. They all have this chemical composition. They're a beryllium aluminosilicate. They all have a hexagonal structure that's described in this thing called a space group. So this describes that 3D lattice. But these all have different gem names. For instance, one variety of a gem name here is aquamarine, but aquamarine is not a mineral name. In this case, technically the mineral is beryl. So if you were to discover some new color of beryl, it would still be beryl. It wouldn't necessarily be a mineral in its own right. It would still be beryl. That's the mineral. So back to these things. It's a solid that occurs in nature as a result of geological processes, has a definite chemical composition, and the atoms are arranged in a specific way that defines the crystal. So this is technically what it takes to be a mineral. And we find minerals all around us. The Earth is a rocky planet, and rocks by and large are made up of tiny mineral grains. So minerals are making up most of the solid portion of the earth. Minerals are very abundant. But why is that? Why do minerals occur at all? When we're talking about solid matter in the universe, it's always made up of atoms. And there are a few different kinds of atoms that are summarized here in this table. This is my periodic table from high school. And these are all the different kinds of atoms that exist in the universe. And when they form solids, they typically don't exist as individual atoms or even just clumps of jumbled up atoms. For instance, you wouldn't just find a pile of silicon atoms just jumbled together. And the reason for this is because they form bonds and try to find lower energy configurations, which turn out to be crystals. So we don't actually have to worry about all of these elements. We can simplify it a bit. If we talk about the Earth's crust, there are actually only a few elements or different kinds of atoms that are very abundant. The two most abundant kinds of atoms in the crust are oxygen and silicon. And in addition, we have aluminum, iron, calcium. These are most of the atoms around us on the surface of the Earth. And these tend to bond with one another in particular configurations. And for instance, if we look at something like silicon and oxygen combining together, they often make silicon dioxide, which doesn't typically occur as just an amorphous lump. It often forms crystals like this. This is quartz, and quartz is one of the most abundant minerals we find in the surface of the Earth. So why is it that the silicon and oxygen kind of bind up and form this ordered pattern? It has to do with sort of saving energy or finding lower energy states. And this is kind of an abstract concept, but I can hopefully tie it into something that's a bit more familiar. Here is a fruit bowl with an orange in it, and I've placed an orange in it here. And intuitively, you know that this is not a preferable energy state. This orange will find a lower energy state. This orange will roll down to the bottom of the bowl. So this is a lower energy state. And here we're talking about gravity. This is gravitational potential energy. But a similar idea applies at the atomic scale. When you have lots of atoms and they're forming a solid, they don't just arrange themselves randomly. They have a tendency to interact with one another. And during those interactions, they're always finding these lower energy states. And in that process of finding lower energy states that are more stable, they form crystals. This is just the way it works, just like the orange rolling down to the bottom. So if we go back to silicon dioxide, here's a clump of silicon dioxide. And this is a glass, so it's not actually forming a crystal, it's all disordered. And this is sort of comparable to this state here, where we've got this orange that's in this perched kind of metastable state. It's not going to stay there. The more sort of preferable energy state, just like the orange going to the bottom of the bowl, would be to form a crystal like this. So here we've got these atoms and they've reconfigured themselves, given the opportunity. This is a lower energy state. If it can form, it will tend to form a structure like this in the Earth's crust. So this is silicon dioxide in its lower energy state, where it just tends to form. So this is silicon dioxide, but for all minerals, we have crystal structures like this that are trying to find this kind of lower energy state. So here's quartz, another view of its crystal structure, and it's got a definite chemical composition of silicon and oxygen. Here's another mineral. This is called halite, but you might know it better as salt or common table salt. This is made of sodium and chloride, and it forms these cubic crystals. Another example of a mineral is ice. When it forms in nature, sometimes we see excellent crystals in the form of snowflakes. And ice is solid water. It's H2O. It has a definite chemical composition of hydrogen and oxygen. And it has a definite crystal composition like this, a structure that it tends to form in. So these are minerals, and there are lots of different minerals around us that we've known about for many years. We've described them formally, and we encounter them again and again. But occasionally, people run into something new. Okay, here's something new here. It's another crystal, and if it has a different chemical composition and crystal structure from the things that we already know about, the things we've already described, then this is potentially a new mineral. But it's not as simple as just saying, hey, everybody, I found a new mineral. There's a formal process on an international scale that goes into describing a new mineral. So who's in charge of this? Well, it's the IMA, the International Mineralogical Association. They have a special committee called the Commission on New Minerals, Nomenclature, and Classification. And as of last month, they have a record or a list of 5,721 valid minerals. So if your new mineral isn't something that's already been described, then it fits that bill. It's potentially a new mineral. So if you have something like this, how does it actually become a new mineral? Well, this material, this new mineral, must be described and characterized in a formal written proposal that goes to the IMA. And you have to describe things like its exact chemical composition, its crystal structure, so how the atoms are arranged in 3D, the occurrence, so where you're finding it, where it occurs in a geological context, and you have to propose a name. And there are some rules around the name. You can't name it after yourself. You can't name it after a corporation. The name has to have some kind of a justifiable significance behind it. Typically, minerals are named after scientists that have had some kind of an outstanding contribution. This is a way to recognize them. So the proposal contains all of these elements, and if it's approved by the IMA and they say, yes, this is a new mineral species, then the next step to finalize this description of a new mineral is to write a paper. So you have to have a published peer-reviewed scientific paper within the next 2 years. When you hit that mark, and you have this paper, then you're done. And then it's formally accepted as a new mineral species. And today we're talking about 2 such new minerals that have been discovered and formally described at GIA. One is crowningshieldite, and the other is johnkoivulaite. So I'm going to start off talking about this guy here, and then Aaron's going to tell his story about the discovery of johnkoivulaite. So beginning with crowningshieldite here, this stems from my work. As a research scientist, I study diamonds like this one and their inclusions, both to understand how diamonds form and both also to learn broader things about the geology of the Earth. There's actually a lot of information contained inside diamonds. So I spend a lot of time looking at all sorts of different minerals trapped inside diamonds. And occasionally, like in this story here, we might come across something new. So I was looking at a particular kind of diamond. I was looking at inclusions in diamonds from a mine called Letseng, which is in Southern Africa here. And this mine is known for producing large, high quality type 2A diamonds like these ones shown here. The largest is 91 carats. And in a geological context, we refer to these as clipper diamonds. It's an acronym that describes their physical characteristics. So clipper diamonds like these are interesting now because in the past few years, we've recognized that these are actually super deep diamonds. So they have an origin that's several times deeper than most other diamonds we know of. These diamonds come from about 360 to 750 kilometers deep in the Earth, almost reaching as far as the lower mantle, this boundary at 660 kilometers down here. So the inclusions in this are interesting for science because they have broad implications about the behavior of the interior of the Earth. And this is the reason why I've spent a lot of time studying these inclusions. So the main inclusion we find in these diamonds is stuff like this, these metallic inclusions. And on the scale of the faceted gemstone, these often look like little black specks, but under higher magnification under the microscope, we can see these shiny, silvery looking shapes that are actually metallic in composition. They're actually rich in iron and nickel. And on the next slide, I can show you a cross section through this inclusion here, and we can see what it looks like inside. So this is a cross section through this inclusion, and the colors correspond to different atoms here, different chemical elements. We've got iron, nickel, and sulfur. And this inclusion has multiple phases within it. So we see three main phases: this bright green phase, which is an iron carbide called coinite. There's this aqua kind of teal or turquoise phase. It's a sulfide, an iron sulfide called pyrrhotite. And then in purple here, we've got this iron nickel alloy. And the interpretation is that this inclusion was originally trapped as a liquid. It was a molten metallic liquid. So I've spent a lot of time looking at inclusions like these, but sometimes you encounter inclusions that have a surface reaching crack in them. And what I mean by that is shown in this cartoon down at the bottom. So here's a diamond, and it contains a very well sealed inclusion that is sealed off from the external environment. But here's another inclusion, and it has this crack that penetrates through it and is actually surface reaching. It's reaching the surface of the diamond. And this means that it's no longer sealed. And if it's no longer sealed, then it's susceptible to alteration. So the inclusion can kind of change a bit. It can undergo chemical changes at the surface of the Earth, or during transport in a kimberlite eruption, or maybe even during residence in the mantle. It could interact with fluids and modify itself and sort of form new minerals. And that's where we're going with this story. So here's an inclusion that has been exposed by the surface reaching fracture, and it has formed some new materials. So this is the actual type inclusion shown here. This is the diamond sample in which we discovered this new mineral here. So it contains little black materials here. These are fresh inclusions that are very well sealed, that are rich in iron, nickel, carbon, and sulfur. So they're just shown in these green colors here. Those are unaltered inclusions. But over on the right here, we've got an inclusion colored in blue here, and this is an altered inclusion, and it's been connected to surface by this big fracture with this reddish staining on it, and it's actually been altered to modify its mineralogy, and now it's composed of fine-grained oxides, graphite, and some kind of a nickel sulfide phase. So here's just a close-up on that particular inclusion, and this is the inclusion we're going to be talking about, where we discovered this new mineral. So one of the first things I did with this inclusion to analyze it in more detail was use X-ray diffraction. And X-ray diffraction is a technique where you pass some kind of an X-ray beam into your sample or crystal of interest. And a lot of the X-ray beam passes right through onto whatever detector you have. But because this sample, if it's a crystal, it has repeating evenly spaced layers in 3 dimensions, it will actually diffract some of this X-ray beam. So you'll get X-rays shooting off into different parts of this detector, and they can form a pattern. And this pattern contains direct information about the crystal structure, how the atoms are arranged in 3D. So this is what I did with our sample of diamond here, and specifically this altered inclusion within it. And this is what the data looks like. So this is the diffraction pattern that we collected from that inclusion. And it contains multiple phases in it. And using some special software, we can try to identify all the different materials that are superimposed on this diffraction pattern. And it's mostly made up of a mineral called magnetoferrite. It's also got some hematite in it and graphite, but it also has this here, a nickel sulfide. And this is something that's in the database that I was comparing with, but it's not actually given a mineral name here because it's not actually a mineral in the database. This nickel sulfide that's in the database is alpha nickel sulfide. And we'll just pull that out on this next slide here. So this is the same diffraction pattern we were looking at. And now we've just marked on here 2 different nickel sulfides. One is beta nickel sulfide, which is a mineral called millerite, and the other is alpha nickel sulfide from this comparison database. We have an example of a diffraction pattern from a synthetic sample. And if you look at beta nickel sulfide in these black lines, we see that if it were present, it would be producing peaks at these black lines, and we see nothing here. Instead, we see peaks that actually match up with these red lines here. And these red lines correspond to the alpha nickel sulfide, which is a higher temperature polymorph that's never been observed in nature before. So this was sort of the aha moment that actually we're looking at something that hasn't been observed as a naturally occurring crystal before. And therefore, this is potentially a new mineral. It might be this nickel sulfide here. So we've got the crystal structure down pat here. The next thing to do was to check its chemical composition, make sure it really is this nickel monosulfide. So here's the sample again. It's been cut down to just sort of isolate this one little part of the inclusion. And we're looking at it more close up now in a secondary electron microscope. This is just part of that altered inclusion. And we're actually going to zoom right in this little red box here and use a technique called EDS, energy dispersive X-ray spectroscopy, to see what chemical elements are present. So here's that zoomed in region here. And we can see, just based on the difference in backscattered electrons, we can see different shades of gray. So this black here, this is due to the diamond itself. There's also black here that's just the carbon present in graphite. There's a medium gray phase here that corresponds to magnetoferrite, but it's this brighter gray phase that we're interested in. So this is what we were seeing in the X-ray diffraction data. And here, using EDS, we can produce this spectrum here that shows the characteristic X-rays emitted by different elements, different atoms that are present in this material. And we can see that it's made up of nickel and sulfur, plus a little bit of iron too. So this allows us to identify what it's made of. So now we have the chemical structure and we have the chemical composition. And we know that this is a naturally occurring solid material. So this is all the things that you need to describe a mineral. And we can actually, at this point, say, well, this is a new mineral, and we proposed a name for it. The name is crowningshieldite. And this is what its crystal structure looks like. So here you can see different atoms that make it up and how they're configured. And these are all the sort of technical specs that are involved with putting together a formal proposal. And we can just sort of ignore them for now because it's kind of complicated. But we can just focus on the fact that we have the composition and the structure now. And this is previously known as a synthetic material, which we called alpha nickel sulfide. But now that we've observed it in nature, it qualifies as a mineral, and we've named it crowningshieldite. So if we kind of look at that again in more detail, this is what its crystal structure looks like. This is the unit cell. So this is the smallest kind of diagram you could draw that still contains all the relevant structural information to describe this sort of material as a crystalline material. And it's made up of nickel atoms, and in yellow here, these are sulfur atoms. And I've also drawn it in a slightly different way, where we've actually built polyhedra. So here we've got, again in gray, these are the nickel atoms, and each nickel atom is bound to 6 sulfur atoms, and this defines a little octahedron. So you can think of this mineral as being built up of all these little tiny octahedron shapes that are nickel atoms surrounded by 6 sulfur atoms. And these octahedra are stacked up face to face along the C-axis of this mineral. So this is the material, we've described it, and the name of it, crowningshieldite, where does this come from? Well, it's named in honor of G. Robert Crowningshield, who was a scientist who worked at GIA. He was a pioneering figure in GIA research for more than 50 years. So a lot of the sort of initial direction and thrust of GIA research came from this gentleman here. One of the things that he did was really push the use of spectroscopy in the identification and characterization of gemstones, and especially diamond. And he actually produced a whole handbook of spectra that he drew out by hand. And this has been an invaluable reference for many, many years. And he also spent a lot of time looking at diamonds, particularly yellow irradiated diamonds, which for a time was a significant concern in the trade, distinguishing between natural yellow diamonds and diamonds that had been treated to turn them yellow. And he was able to use spectroscopy to distinguish between the two very rapidly and with low cost using the spectroscope. So this is his legacy, and now Crowningshield, G. Robert Crowningshield, is sort of honored in this new mineral name. And then the final step in making this new mineral is the publication part. And this is where I should really highlight the people that have helped me put this story together. So that initial X-ray diffraction work that I did alongside Fabrizio Nestala, who's a professor at the University of Padova in Italy. And some of his colleagues also helped to characterize this material and put it together into a formal publication. So this was published earlier this year, and this is the final step in making this new substance that we've discovered, making it into a formally accepted new mineral. So that's the story of crowningshieldite. And now we can move on to the next story of a new mineral discovered at GIA. I'll pass it over to Dr. Aaron Palke.
Thanks, Evan. All right, so the next story, as Evan said, is about johnkoivulaite. So johnkoivulaite starts here. In late 2018, a unassuming stone, you're seeing it on the right there, that's the stone. It was about 10 to 5 millimeters in size. It was submitted to the GIA Bangkok lab for a simple routine identification report. So here at GIA, one of the services we offer to the gem trade is identification reports. And so if you send in a stone, we'll tell you what it is. We'll tell you if it's been treated, if we can, and all these other sorts of things. This service is generally relegated for gemstones. And so, you know, a gemstone is something that's aesthetically pleasing, that's used for personal adornment. And so I think one could potentially argue that there's a little bit of leeway and a little bit of subjectivity in that definition. So sometimes we do get very unusual stones in for identification reports, which, you know, you might argue about whether or not it's a gemstone, but we get some very unusual things sometimes for these identification reports. But regardless, any stone that's sent in for a report, obviously we treat it with the same respect as any other stone we deal with. So the pebble you send in, we're going to treat it with the same respect as you know, the sapphire that somebody else might send in. And so we'll run through the whole series of analyses. We'll do everything to your stone for the identification report that we would do for any other stone, including the gemological analysis and advanced spectroscopic and chemical analysis if needed. And so we started looking at this stone, this unassuming kind of stone that was sent in. And we started realizing that we did the gemology, we did the refractive index, the specific gravity, optic character, all of these optical techniques to look at the stone. And it didn't really match any known gem material that we're familiar with. We turned on to some spectroscopic analysis, but that also sort of failed to produce a match to identify the stone. And so I'll show that here. This is the Raman spectrum of that stone. So Raman spectroscopy is this technique we use, especially for stones that are hard to identify, where the gemology doesn't, the gemological testing doesn't really identify conclusively. We'll turn towards advanced testing like Raman spectroscopy. It's a way of getting a fingerprint of a specific mineral. So most minerals will have kind of a unique Raman signature, which is based on their vibrational properties. Different minerals vibrate differently than other minerals. And so each mineral gets its own unique little Raman fingerprint. So on this slide, we're seeing in blue, that's the Raman spectrum of this unknown mineral that I mentioned. And on the bottom is the closest match that we got when we put that Raman spectrum through this algorithm in the computer. So we take the Raman spectrum, put it in the computer, and it generates what it thinks is the best match for our unknown mineral. In this case, it matched us with beryl. That was the closest match. But it's even for beryl, it's obviously not a very good match. There's obviously a lot different between the beryl spectrum and this unknown mineral. And so all of a sudden we started realizing this might be something different that we've never really seen before. So we went a step further and said, not only is it not really any gem material we've ever seen before, but the properties of this stone don't really match any known mineral species that's ever been described before. And so we started realizing that we were going to need to do some more kind of advanced analytical techniques to kind of get at this to characterize this material more thoroughly. So as kind of shown here, like I said, the closest match was beryl, but again, the properties didn't really match. The specific gravity was different. the refractive index was different, the birefringence was different. They both had this uniaxial optical character, but besides that, there wasn't a whole lot to really go on. So at this point, we took the stone outside of GIA, and we realized we needed to collaborate with colleagues from Caltech. So we were working with Chi Ma and George Rossman, as well as another fellow, Lawrence Henning, who is a single crystal X-ray diffractometer expert. And they all helped us kind of characterize this material a little more carefully. Now, the first thing we did was this technique called electron backscatter diffraction. And this is very similar to what Evan Smith mentioned about the X-ray diffraction. But instead of X-rays, we're using an electron beam. So when you shoot an electron beam at the sample, the electrons can actually act like waves, just like X-rays can. And so those waves that we hit with the electron beam onto the sample, they diffract off of the different crystalline planes within the material. And each material, because it has a different mineral, because it has a different unique set of crystallographic planes in it, it gives off its own unique fingerprint in the EBSD analysis. And you'll see that here, this is the output of the EBSD measurement. You see these kind of faint lines going through this structure. These are the diffraction lines coming off the material. And what you do with EBSD, you can index those lines against your known reference database. In this case, the closest match was with beryl or other minerals closely associated with beryl, so other beryl group minerals. And so we found, again, this structure is going to be very similar to beryl probably. The Raman spectrum was pretty close to beryl, and the EBSD was pretty close to beryl as well. Now, the next step, though, we had to do some chemical analysis. So if you're going to describe a mineral, Evan touched on this as well, you need both the structure and the chemistry. And so we turned to electron probe microanalysis in order to measure the chemistry of this stone. And what we found was that the chemistry is obviously very different from what you expect for beryl. So in this case, we have a lot of magnesium, we have some boron in there. We're missing that aluminum that you expect to see in beryl. And so this result that we got from the electron probe microanalysis. These numbers are given in terms of what we call weight percent oxides, which is a unit that geologists like to use a lot because a lot of the rocks in the Earth's crust are oxide minerals. And so it's kind of convenient to think of things in terms of weight percent oxides. However, it's not very informative about what the actual chemical formula is. So if we reduce this chemical formula with the assumption that it's something in the beryl group, and we have some pretty good evidence to suggest that it's a mineral in the beryl group. So we can use this information to kind of constrain the chemistry of this material. So we know beryl group minerals have 18 oxygens and 6 silicon atoms in their chemical formula. So if we take the data above and reduce it to the chemical formula, as measured, we get something that looks like this. It's pretty messy because there's a lot of different chemical elements going on in there. But we see the 6 silicons, the 18 oxygens. We have a lot of magnesium in this particular site where you expect to see aluminum. In the site where you have only beryllium and beryl, we have some boron in there as well. And then we have this additional crystallographic site where there's a lot of cesium, potassium, and sodium, which is not in the ideal beryl formula. But what we can do with this, these sites are dominated by a certain element. And so we can take this and simplify it a little bit. We can give an ideal formula to this new mineral. And that's here. So the ideal mineral formula is cesium, beryllium 2, boron, magnesium 2, silicon 6, O18. And so again, this is fitting that beryl formula very well, but it's got a very different chemical formula from the beryl. And we're going to get into a little bit of that more in a few slides when I talk about the kind of mineral groups and that kind of means. So all of a sudden we have both the structure and we have the chemistry. And I didn't touch on it too much, but we also did single crystal X-ray diffraction on this mineral. And that's a way of getting a much more accurate and precise chemical structure than you can get from the EBSD alone. But the basic results are here. So we were able to take this data, submit it again as a proposal to the IMA, and we got the mineral accepted with this name, johnkoivulaite, with this ideal chemical formula shown here. It's a mineral in the hexagonal crystal system. It's got the space group P6 over MCC, and that's just describing basically the symmetry elements within this mineral, how the different atoms relate to each other in the mineral. And we were able to measure the lattice parameters as well of this new mineral. In terms of the gemology and mineralogical properties, the new mineral has a hardness of about 7. A streak is colorless streak, vitreous luster, a specific gravity of 3.117, refractive index of 1.605 to 1.607. It's uniaxial in birefringence of 0.002. And now actually one of the really unique things about johnkoivulaite is that most new minerals that are submitted and accepted these days, you can't really measure these properties because most new minerals are these very small microscopic pieces that we find in meteorites or unusual rocks in the earth. Johnkoivulaite's very unique in that this is actually like a macroscopic mineral. You can hold it in your hands and you can look at it and you can do a scratch test and you can measure the luster and the streak and all these other things. Most of the minerals that are like that, where you can make those measurements, have already been described in the past because those are sort of the easier minerals, the easier new minerals to be able to describe. So johnkoivulaite is really sort of unique in that regard in terms of new minerals these days. One of the most striking things about johnkoivulaite, and one of its kind of defining characteristics, is its pleochroism. And this was actually a little bit of a surprise to me because the birefringence is actually very small. So the difference between the refractive index in different directions in the crystal was 0.002. That was far too small for us to be able to measure accurately on our standard gemological refractometer. We actually had to work with Tony Kampf at the Los Angeles Museum of Natural History. He has specific refractive index matched oils that he was able to use to measure the refractive index very carefully. But despite this very small birefringence, it does have very different optical properties in terms of the way it absorbs light in different directions. And so what you're seeing here in these two photos is johnkoivulaite in the microscope with a polarizing filter. And the polarizing filter has been rotated 90 degrees between these two directions. And you can see the color goes from almost colorless in one polarization direction to this very deep, rich, vivid violet color in the other direction. And so I thought that was very unique. And that's kind of one of the defining characteristics of this new mineral. Now, as to why we named it johnkoivulaite, so this was named in honor of John Coivola, one of my mentors, I guess, to an extent, and one of my good friends here at GIA. He still works here, and we always were, happy to have him here in the lab where we can ask him questions about different minerals and different things about the microscope any day that we need to. Now, one of the things John was really famous for was advancing and really revolutionizing the use of microscopy in a very scientific way for studying gemstones. And so he's responsible for the way we look at gemstones in the microscope today. Almost anybody who looks in the microscope really at a gemstone is standing on the shoulders of John Coivola, who introduced a lot of new techniques and a lot of ways of thinking about inclusions in gemstones. And also for all these very beautiful photomicrographs he produced of inclusions in gemstones, which I think has really propelled the science of microscopy in gemology today. And so, we named this in honor of him because of all of his contributions to the world of gemology. Now, we're going to talk a little bit more about the structure of these johnkoivulaite, and I'm going to go into a few more details and compare this to some other minerals of the beryl group family. But first, we want to talk about the structure of johnkoivulaite. So if you've ever seen some atomic diagrams of different crystals, this might look familiar. If you've ever seen the beryl structure, this looks very similar to the beryl structure. So what we're seeing here, and Evan talked about these polyhedra units that we have in these crystal materials. These are, in this case, these are polyhedra with a cation at the center of the polyhedra, surrounded and bonded to oxygen atoms. So the oxygen atoms are shown in red. These red spheres here are oxygen atoms. And around each of these polyhedra is a specific type of atom. So in this case, the defining characteristic of the beryl group minerals is these rings of silica tetrahedra. So these are 6-membered rings of silica tetrahedra. They have the kind of formula Si6O18 because there's 6 silicons forming these rings with 18 oxygens forming the tetrahedra. And they're stacked along the C-axis. You can see that there's actually, you can see kind of 12 tetrahedra here. That's because they're stacked and they're kind of askew as they're being stacked down the C-axis. They're connected to the other silica rings by these distorted tetrahedra of beryllium or boron in the case of johnkoivulaite, and also these octahedra with magnesium occupying these octahedra. The thing about johnkoivulaite is we have boron and beryllium on these green distorted tetrahedra, and it's completely disordered. They're randomly distributed throughout that site. In addition to those atoms, there's also in the middle of these silica tetrahedra rings, these atoms of cesium, these big atoms of cesium that are occupying these channel sites. And that's shown again here. One unique thing about johnkoivulaite in the beryl group minerals is that this site where the cesium sits, we call it a 2A site. It's a specific crystallographic site where the cesium likes to sit. Now, a lot of beryls actually have a fair bit of these alkali ions occupying these channel sites. these 2A sites. But in most cases, the amount of the alkali ions occupying that site is less than 50%. So it's usually typically very low in terms of the overall amount of alkali cations occupying those sites. And what happens in Beryl, since if you have very little occupancy of that site, nature doesn't like a vacuum, right? So something typically tends to go into those channel sites because this is this big empty space in the structure. And so typically what happens with Beryl group minerals is you stuff a lot of water into those channels in between those silica rings. In the case of johnkoivulaite, this site is occupied by almost 96% occupancy. And that means that in terms of other Beryls, johnkoivulaite is a very kind of dry Beryl group mineral. There's not very much water because you can't really stuff much water when you have stuffed those sites with all that cesium in there. And so we can kind of call johnkoivulaite like a stuffed Beryl group mineral. Now, one question is, so all of this data we collected so far, this was on one single crystal that was submitted to the lab. And it was submitted on behalf of this fellow Namio, who is a gem dealer from Mogok, where the stone was originally recovered. And he's actually, we should credit him as actually being the person who really identified this stone as being something new in the first place. He's the first person who really discovered this and realized that it was something new and different in the mineral world. There's this rich history of gemstone mining in the Mogok Valley, where they produce a lot of the best rubies and sapphires in the world. And so the people in Mogok actually have a very astute and keen knowledge of minerals and gemstones, even though most of them have not been formally educated in terms of getting a geology degree, that sort of thing. There's actually a wealth of mineralogical and gemology knowledge in Mogok just because of their familiarity with all these various different gemstones throughout the years. And so this was all done on that single crystal that was submitted to the lab. We visited with Namio in 2019. And he actually showed us a second piece of johnkoivulaite that he had been able to procure. The johnkoivulaite was recovered from the Pine Pit mining area in Mogok. On the left is this second piece of johnkoivulaite that he was able to procure. And you can see this is seen through a dichroscope. So this is a polarizing filter with the polarization direction at 90 degrees to each other on both sides of that line. And you can see that kind of characteristic Pleochroism in this second piece of johnkoivulaite. So there's at least one more piece of johnkoivulaite out there. If I had to guess, I'd say there's probably more in that Pine Pit mining area. It's probably not only 2 crystals that ever formed existence. But so far, to the best of my knowledge, nobody's really produced more of this material yet. Now, I talked a lot about Beryl group minerals, and that just kind of leads me to one thing I wanted to talk about a little bit, which is this concept of mineral groups. So johnkoivulaite is the 6th member of the Beryl group family. It joins beryl, pizodite, basite, stopaniite, and avdeevite. Interestingly, avdeevite was also produced in Myanmar, not too far from Mogok in the town called Momaik. And so it's actually kind of interesting that there's these 2 new members of the Beryl group family found pretty close to each other in this kind of unique geological area. So what is a mineral group? And I'm going to go back to what Evan kind of touched on in the beginning, what makes a mineral. So a mineral has a naturally occurring solid. It has a particular chemical composition, and its atoms are arranged in a specific 3-dimensional pattern. So the thing is, though, with a new mineral has to satisfy these criteria, and it also has to be different from any other mineral that's ever been observed. But it doesn't have to be different in both of these properties of chemistry and structure. So for instance, with diamond and graphite, these both have the same chemical composition. They're just carbon. But they're both 2 distinct different minerals because they have a different atomic arrangement of their atoms in that structure. So likewise, 2 different minerals, 2 very distinct minerals, can have a very similar overall atomic structure as long as they have different chemical compositions. And that's shown here with this example of andradite and spessartine garnets. So these are 2 garnets in what we call the garnet group. And you can see from their structure below, they have very similar very similar atomic arrangements in terms of the different types of polyhedra they have and the topology of the way those atoms are arranged and related to each other. But they are distinct minerals because, for instance, in this big, what we call a dodecahedral site, shown in green for andradite, we have calcium and we have iron in the octahedral site, whereas in spessartine, we'll have manganese in that big dodecahedral site and aluminum in that octahedral site. And so this difference in chemistry, the difference in the atoms we're putting in that overall similar structure, is what makes these 2 different minerals belonging to one mineral group. Now with the beryl group, we're going to talk about a few different examples, just to kind of illustrate these different properties and the way we describe these different minerals group. So some examples are johnkoivulaite, basite, and beryl, 3 different minerals in the same mineral group. Now, the easiest way to illustrate this is to compare 2 of these minerals. So we compare beryl and basite. They actually have a pretty similar overall composition. Beryl is beryllium, aluminum, silicon, and oxygen. And you see the aluminum occupying that octahedral site in the beryl structure in that light blue octahedron. To make basite, you would substitute scandium for all that aluminum in the structure. Now on the right, you see basite with scandium in that pink octahedral site. And that's what's making these 2 different minerals with the same overall atomic arrangement of their atoms within that mineral group. Johnkoivulaite's a little more complicated. You can see when we go to johnkoivulaite from beryl, we have to make a few more different substitutions. So we're substituting a magnesium in johnkoivulaite for the aluminum in beryl. We're substituting some boron for some of the beryllium in the that distorted tetrahedral site in beryl. And we're also adding an atom to this channel site in between those silica rings. Now, Pizodite's actually kind of similar to johnkoivulaite in terms of its the complexity of its chemical formula and its differences from beryl. We see with Pizodite, we're substituting aluminum for magnesium in johnkoivulaite, and we're substituting lithium on one of these distorted tetrahedral sites for the boron in johnkoivulaite. And what you'll see in Pizodite, these distorted tetrahedral sites actually get split into distinct crystallographic positions or crystallographic sites. And so you see this site is split. We have these green distorted tetrahedra, and we have the red distorted tetrahedra. And what happens with Pizodite actually has a different, what we call a space group than johnkoivulaite and other members of the beryl group, which means it has a different symmetry. So the symmetry is actually lowered in Pizodite versus johnkoivulaite. So in johnkoivulaite and other members of the beryl group, we have this 6-fold rotational symmetry within those silica rings, where you can see that you could rotate the crystal structure 6 times until you get back into the original orientation. And each time you rotated it, you would have the same crystal structure. You would be looking at essentially the same crystal lattice. With Pizodite, because we're splitting those sites apart, we can only rotate the crystal structure 3 times before getting back to itself because some of those sites are split. Now, I want to kind of end on just one last kind of short story, which is the story of Pizodite. And actually, GIA was sort of involved in the description and the discovery of Pizodite as well. So Pizodite was discovered in November 2002 in a pegmatite near Ambatavita, Madagascar. It hit the market in 2003 at the Tucson show. It was marketed as cesium-rich beryl, or I think some other terms thrown on were like raspberyl or raspberry beryl. So people already had this idea that it was probably something similar to beryl, but they knew it was something different, of course. And so when people started studying this new mineral in the lab, we realized that it's actually not beryl. Its properties didn't match with what you expect for beryl. So the refractive index, specific gravity, all those things were kind of off. And actually, in 2003, February of 2003, some of those first pieces of Pizodite came into the lab at GIA. So I think johnkoivulaite actually brought the stones in, and he gave them to Dino DeGano, who's shown here. Dino DeGano is shown here at the Xray diffractometer we used to have at GIA back in the day. And so while we use Raman spectroscopy to identify unknown minerals today, back then they didn't have Raman spectrometer, so they would have turned towards X-ray diffraction. And so what you would see, this was an older unit where they actually used actual film in this canister that Dino is loading. So he's loading up a little bit of a small bit of this mineral on a spindle inside this canister. He would have put film around the outside edge of that canister, and they would shoot X-rays into this stone, and then you would get a diffraction pattern on that film. And so this is what Dino did with this new mineral that came in. And I actually went through the archives we have here and dug up the original X-ray pattern that Dino had collected on this Pizodite in February 2003. So this is probably one of the first X-ray diffraction patterns, if not maybe the first, to ever be collected on Pizodite in February 2003. And so this looks a little bit different than what you saw with Evan's examples of the X-ray diffraction patterns, but what you're basically seeing is those diffraction lines in these circles around the center of this film. And each different mineral would have its own unique fingerprint in this X-ray diffraction pattern that you could use to identify the mineral. And so because people had already realized this is probably like a beryl group mineral, they compared this pattern to the beryl reference pattern. And what they saw was that there were some obvious similarities between beryl and this new cesium-rich beryl. Some of those lines line up pretty well with each other, but they also noticed some pretty significant differences. So they started to realize that some of these lines have a higher intensity in this new mineral than they do in beryl. And in some cases, those lines are not only more different in intensity, but they also are kind of shifted in position on the diffraction pattern. So they started to realize that this was probably a new mineral. And so Dino and John didn't actually really get to follow up on this description of the new mineral, but one person who was at GIA at the time, Brendan Lars, he was the editor of Gems and Gemology at the time. He was actually involved in the description of Pizodite as a new mineral. It was named after Federico Pizota, who's the curator of the Natural History Museum of Milan. And this art, it was an article published in Gems and Gemology. It was not the actual type description article, but there was an article about the history of Pizodite and how this mineral was named and described and discovered in the winter 2003 issue of Gems and Gemology. So if you have some time, it's a great article to go through and kind of learn the story of how a new mineral is discovered. Now, one final thing before we sign off and get to some questions is just a brief note about some other notable GIA-related new minerals. So through the years, we've had some very prominent scientists and researchers associated with GIA who've had minerals named after them because of their contributions to the science of mineralogy and gemology. One of the most prominent is lidocotite, which is named after R.T. Lidicote, a former president of GIA. This is a member of the tourmaline supergroup of minerals. We've had minerals named after several people who are on the board of governors at GIA. So the first one is Ewingite, named after Rod Ewing. This is a uranium-rich mineral, and that's as fitting because Rod Ewing was famous for studying radioactive materials in the earth. He's a professor at Stanford University, and I read on MinDat, Ewingite is has the most complicated crystal structure of any known mineral, and you can kind of see that with these huge number of different components that they would have to fit into this crystal structure. The next is Valleyite, named after John Valley, professor at University of Wisconsin, who is a current member of the GIA Board of Governors. And finally, Dutroite, named after Barbara Dutro, another mineral in the tourmaline supergroup, which is fitting, of course, because Barb Dutro is the expert in the world on tourmaline minerals. She's a professor at Louisiana State University and a current board of governor with GIA. And so with that, I think we can open it up to some questions, and I hope we can answer some kind of interesting questions.
All right, Dr. Palke and Dr. Smith, thank you so much. I know I thoroughly enjoyed that and learned quite a bit. Let's just start off with some questions that we've recently been submitted. We have this question from an anonymous attendee. Among new mineral discoveries, do you think some of them will be used in the jewelry industry, or do you have an example of a new mineral that became known to the public and is known to the jewelry industry?
Yeah, so I think probably the best example of that is actually Pizodite, which was discovered in the end of 2002, described as a new mineral in 2003. And it's still a relatively rare gem mineral, but you do see examples of this as a faceted stone. So once they hit this pocket, they were able to produce a lot of this material and bring it to market and start cutting it into stones. It's still kind of a collector mineral, but that's probably the best example of that. Now, John Coivolite potentially has the potential for becoming that sort of thing as well. Unfortunately, only 2 pieces have been discovered, but there might be more of this material out there in Mogok that could be eventually, used for gemstones.
Awesome. Let's do a couple more questions about Pizodite. Who proposed the name for Pizodite? And can you tell us a little bit more? Is it actually a beryl? What does cesium-rich beryl mean? If you guys can clarify some of that.
Yeah, so Pizodite was, I think the lead on that was maybe Skip Simmons. I don't know exactly the history of who proposed that name, but so that group of authors that was on that paper in Gems and Gemology, that would have been the group of people who had just decided on the name for that mineral. And so the original name that people were calling it, they were calling it a cesium-rich beryl because it didn't have a proper mineral name at the time, but people knew it was sort of like a beryl. So that's actually not a very technically correct way to describe Pizodite. You could say that Pizodite is a member of the beryl group, which means that it's a member of this group that has minerals with very similar overall atomic structure, but different chemistry. And so that's probably, so Pizodite's a member of the beryl group, but it's not beryl.
Got it. Okay, let's, quick question for Dr. Smith. Can you tell us a little bit more about Clipper? What does Clipper mean? I think we kind of just glossed over that, but I know it's important to the diamond.
Yeah, I did gloss over it to save time. I didn't think anyone would be that interested. Clipper is an acronym that describes what have typically been known as type 2A diamonds, but specifically these large, high color, often D color, very high clarity type 2A diamonds. So Clipper is an acronym. The C stands for Cullinan, which is the best example, sort of the type example of diamonds like these. It's a 3106 carat diamond, the largest gem diamond ever found. And it's this exquisite clarity and color. And from a geological context, diamonds like that form in a different way. So that's why they're sort of broken out as a group because of their paragenesis. The way they form is different, but they're still diamond. Those aren't a new mineral.
Okay, let's do a quick question here about garnets from Roy. Why do garnets have such a high refractive index? Some minerals have high RIs because they have heavier elements that are more polarizable, but the garnet family does not have this characteristic with family members such as andradite. I will give that to either of you two to tackle.
That's, yeah, Evan.
Well, I was just going to say, I mean, the sort of heaviness of the atoms is one thing, but sort of the density, how close together they are, sort of affects the refractive index or the optical density of a material. Another example would be diamond. Diamond's made of carbon. Carbon's a very light element, but the carbon atoms are packed very closely together. So the refractive index of diamond is very high. I think garnet is maybe less extreme, but similar kind of situation.
All right, we have kind of a housekeeping question here. I'm aware that GIA has opportunities for postdocs. Are there potential research opportunities for current graduate students?
Yeah, we do. So in previous years, we've had also an internship program. We didn't this last year because of the pandemic situation, but we do intend to bring that program back to life again in coming years. So you can reach out to me and Evan, and I'm sure we'd be happy to discuss that more with you. We do intend to have internship programs for graduate students and also undergraduate students as well in the future.
All right. We've got a quick question about johnkoivulaite. Where is that structure description found?
There's a paper that's in press with the Mineralogical Society of America in American Mineralogist. And so it would be found in that paper in American Mineralogist. If you reach out to me, I'm happy to share that paper with you if you're interested in the structure.
All right, we've got another question about johnkoivulaite. How do we know that such a single crystal specimen is natural and not lab made when you're getting something kind of new into the lab? Can you tell us a little bit more about that process?
Yeah, that's a great question, actually. So the johnkoivulaite, it was, found in the lab. It had no geological context behind it, right? So it's not like the diamond inclusion. Obviously, Evan's mineral was natural because it was found in a diamond that was mined in the earth. So there's a lot more geological context there. But with johnkoivulaite, you're right. We don't really have that. What we do have and what we use to convince ourselves that this was a natural mineral is both first inclusions and also the morphology on the surface of the crystal. The inclusions look like natural inclusions. And so there was no indications from the inclusions or the morphology of the crystal that it was a synthetic crystal. And so we were convinced basically a lot on inclusions and observations of the gemological properties of the stone.
All right, well, I think we're at the point we're gonna have to wrap up our talk. First of all, and most importantly, a big thank you to Dr. Palke and Dr. Smith for their time and preparation today. These talks are always fantastic, and I know many of my colleagues like myself look forward to knowledge sessions. To everyone watching, if you have any additional questions, please look us up on Instagram, Facebook, or LinkedIn. We'd love to hear from you. And thank you for everyone for joining us today. We really appreciated your questions and your interaction. Just a friendly reminder, in 2 weeks, we will have another talk with Dr. Sally Magana and Nicole Aline, all about gemology through the years and interesting discoveries from the GIA laboratory. Thank you so much for joining us, and we hope to see you in 2 weeks.